So on the previous class, we had this moving pendulum differential equation after linearization, and I said that this is the noise, but if the noise is the impulse, as I defined it mathematically, so we don't have x dot. That's why we have to move from time domain to frequency domain, and we define the s as j omega, and the omega is characteristic frequency. So we said the Laplace of a function in time domain is f of s, and this is from 0 to infinity e minus st f of t dt. Okay, so the first case that we have to know, if as we had the case, real case, is f of t is impulse, and based on the definition, impulse is when t is 0, it's unknown. When t is not 0, is 0. And when we plotted this, remember, so it was like this. Here we go. So if you put this definition here, again, your Laplace sucks. So what I'm going to do, I'm going to play with that. I'm going to open this area a little more. I'm going to magnify this like this. Because I said impulse is a huge amount of force, or whatever is in value, in a very short amount of time. I'm saying that short amount of time as delta tau, a very, very small amount of value of the time. Here is time, and this is delta of t. That's right. This is definition of the impulse, like as the boxing. And a very large value. This large value. When delta tau is very small, this is gonna be very large value, delta tau. That's right. See what I'm saying? So now a Laplace of impulse gonna be, I'm gonna divide this integration into two parts, from 0 to delta tau plus from delta tau to infinity. That's right, to infinity. So it's gonna be e minus st, okay, f of t dt, and again e minus st f of t dt. So this delta tau is very small, guys. So means that delta t is almost 0. Okay, almost 0. So that t is 0, it's gonna be 1. That's right. E to the power of 0 is 1. So f of t, so integration of f of t dt means the area under the curve of this. What's the area under this, in this rectangular area from high school or middle school? What's the area under this rectangular area? If you have rectangular from kindergarten, here is AB. What's the area of this? What's the area? Huh? What's the area of the rectangular from? Yes. A times V. So now what's the area of this rectangular? Delta tau in 1 over delta tau. What's the area? Yes. So this is 1. And after this, delta tau f of t is 0. See here? 0. So this is 0. So the Laplace of impulse is 1. We got it. Simple like that. So the first rule, you got it. That Laplace of impulse is 1. Here we go. You found it. Here we go. Okay. The second input, can I go to next page? Everybody? Yeah. So you don't have to go over this. You have to just, you can find this even in the Google. Yeah, also in MATLAB. I'm going to show it to you. Okay. So the second input that is very important in control domain is if f of t input to the system is unit step. That's right, unit step. Like what? Like the temperature of the room. That, or step function. You want to keep it at 75 degrees. Okay, it's a unit step. I'm sorry, it's step function. Or you want to keep your speed of your car by the cruise system to, I don't know, 65 miles per hour. That's a step function. Okay, for your car, step function, you want to keep it here, 65. Or for your room temperature, you want to keep it as 75 degrees Fahrenheit. That's right. But unit step means this, for simplicity, means 1. 1. And before this is 0. That's right. 1. So Laplace of that, Laplace of f of t, gonna be integration from 0 to infinity e minus st unit step dt. Unit step between 0 and infinity is how much? 1. Just put 1. So we're gonna put from 0 to infinity e minus st dt. From high school, it's gonna be 1 over s integration e minus st from 0 to infinity. So if you put there 1 over s e to the power of minus infinity e in power minus 0. So 1 over s, this is 0, this is 1. So that's the answer. Always unit step Laplace transform is 1 over s. Eventually you're going to memorize it. So Laplace of unit step is 1 over s. Here we go. You got it? So third that I told you, ramp. F of t is t, is ramp. Suppose that you want to increase the speed of your car from 0 to, I don't know, say 65 miles per hour linearly. This is the desirable input that you want to follow, that's right. Is ramp. This is t. So we know the Laplace of that, Laplace of ramp, gonna be from 0 to infinity t e minus st dt. So this is part by part integration, right? I'm gonna just do this for you, but the rest I'm gonna conclude. So you know that integration of u dv from high school is uv minus integration of v du. So I'm gonna say t is u and e minus st dt is dv. So you have to integrate. So t, so this is gonna be dt. Let me do like this. It's gonna be dt after integration is du. I'm gonna put here. And here you can, by integration, is differentiation. Integration gonna be 1 over s e minus st. So this is equal to uv. This is your u, this is your dv. uv, u is t, Your v is this, minus over s e minus st, minus integration of v du, 1 over s e minus st in dt. Okay, obviously this is from 0 to infinity, 0 to infinity. Okay, if you replace anything here, the answer, I'm gonna give it to you, simple. Answer gonna be, I'm assuming that, gonna be 1 over s squared. Just you have to know this, not the how we derive that. Can I go ahead? So 4 that I promised in the previous class, if your function or input to the system, I'm going to show in MATLAB Simulink throughout the semester, is parabolic. There we go. So accept from me, because I'm going to skip the math, Laplace of this integration from 0 to infinity parabolic e minus st dt is 1 over s cubed. You see that, guys, by having unit step is 1 over s. By t to the power of 1, we get 1 over s squared, 1 plus 1. By t s squared, s2 plus 1, s cubed. So it means, oh, I have to open a new PowerPoint. Screwed. So it means you can have a general rule that if function is t to the power of n, Laplace of that, Laplace of y, gonna be, let me change it, n factorial s to the power of n plus 1. Let us examine this. As we had the parabolic input, your n is 2, that's right, your n is 2. So gonna be 2 factorial divided by s to the power of 2 plus 1. That's right. Right. And obviously you have a 1, 2 from here. Right. So 2 factorial by 2 gonna be 1 over s cubed. So this is general rule. Now, for example, if I give you what's the Laplace of t to the power of 6, answer is 6 factorial divided by s to the power of 7. There we go. So, case number 4, 5. If f of t or y of t is e minus exponential term, what's the name of this in mathematics, guy? Do you know that? What's the name of this? Mathematics. If I plot this y over time, you have to know its name first. At t0, it's gonna be 1. At t infinity, it goes to 0. So its names correspond to the graph. The name is decaying term. Decaying term. So Laplace of this, Laplace of yt, integration of 0 to infinity, e minus at, this is function, e minus st dt. And from high school, you know that you can combine them, right? 0 to infinity e minus a plus SAT dt. And we already got that. That's right. From high school it is S plus A e minus a plus AT from 0 to infinity. And you know the answer is, for God's sake, 1 over S. Well, I'm changing the color because I have a point here. S plus S plus A. I'm sorry. S plus A. If you have E plus AT, here is plus. It's gonna switch the sign here. It's gonna be minus. You got it? What I'm talking about? If you have E minus AT, gonna be 1 over S plus A. If you have E plus AT, gonna be S minus A. You got it? For example, if Y E 10t, its Laplace gonna be 1 over S minus 10. Here's plus, here's minus. Or if you have Y is E minus 9t, so you have f of S is S plus 9, because here's minus, here's plus. You got it, everyone? Yes? Okay, can I go to the next page, for God's sake? Now, what was that? 1, 5, 6. If you have a given function, guys, let me plot it here for you. Suppose this is a function. Now, if I ask you, you know what? I have this value, f of t minus t naught, means this exactly the same. What I have done to this mathematically, what's the name of this in the literature of mathematics? You see exactly the same. Here is t naught. What I have done, and this is time. What I have done mathematically. Come on. The name of this is delay. You see the same graph. With the delay happens t naught times after that. Clear? So when you see this notation, means delay. 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 So if Laplace transform of the original function is f of s, Laplace transform of the delayed function gonna be e minus s t naught f of s. That's another formula you have to know. The delay effects in the frequency domain is like this. You got it? Let me give you an example. Suppose the function is this, parabolic, as we derived. We know that the Laplace of this, Laplace of parabolic, is 1 over s cubed. Now you know it. What if I say calculate Laplace of y t minus 3? This is y of t, that's right. Means we have 3 seconds delay. 3 unit of time delay. So it's gonna be E minus 3s, because this is T naught. This is T naught. I'm just putting here. In f of s. F of s, we already got it. 1 over s cubed. So the answer is E minus s divided by s cubed. Another example is that if your y of t is e minus 2t, what is Laplace of t minus 5? Laplace of t. We know that you now learned that the Laplace of y of t from whatever I taught you, here is minus going to be plus 1 over s plus 2. So the Laplace of delayed exponential is going to be e minus 5s divided by s plus 2. Clear, everybody? Yes? You got it? Good. Now, number 7. Number 7. I promised you that we have many important input to the system that you're going to see throughout the semester. Impulse, unit step or step, ramp, parabolic. Another things that is very important is the harmonic input to the system. Sine omega t or cosine omega t. We're going to use this in the body plot. I'm going to teach you in a couple weeks. Body plot by mathematics and in MATLAB. You're going to tell me, are you stupid, Payman? No, I'm not stupid, okay? So suppose that for the rotor dynamics in machinery, you wanted that the rotor goes from the speed of 0 to speed of 10,000 RPM. Or for the engine of the airplane, you want to go from to 0, I don't know, to say 5,000 RPM. See, there you have a frequency you want to reach, you want to follow. So this is another input, another desirable input that you wanna follow this, right? So we're gonna go over this body plot, and I taught this in math in the vibration in another form in the previous semester, but in control is different. So if y is sine of omega t, and remember, even in the vibration course, I said that omega is excitation frequency, external excitation frequency. You are exciting the system from excitation frequency. So Laplace of that, Laplace of f of t, gonna be from 0 to infinity, e minus st again, sine omega t dt. Again, you have to go part by part integration. I'm not using that, so you give me the final answer. Omega in s square plus omega square. Very good. Even sometimes this can be disturbance of your system. Let me teach you that to experience maybe sometime by your car. If this is simplified model of your car, mass, spring, and damper, suspension of your car, and this is your tire, and this is this harmonic profile of the road that you are traveling on, sometimes in the suburb. So this is disturbance to the system, this sign. So if you want to take it to frequency domain, so it's going to be like that. You got it? Example of that is very easy. If the y is sine of 5t, you know that the Laplace of y, so your omega is 5 radian per second. This is radian per second, 5 omega. Gonna be 5 divided by s squared plus 25. Now, what if I say calculate Laplace of t minus 10? What does it mean again? I just taught you. What does it mean again in mathematics? Huh? Yes, delay. So you know that this Laplace of this, Laplace of y t minus 10, when your y is this, gonna be e minus 10t multiple f of s. F of s we already calculated. Gonna be 5 divided by s squared plus 25. Let me write it clearly because it's confusing. Here is 5. See? Interesting, right? Hmm? What? This? This is the unit. A frequency unit is in radian per second, that's right? From vibration course. Or yeah, even dynamic course, ME220. Yeah, I just wrote this unit, that's right? Omega. Right? Okay. Can I go? Yes? Okay. Number 7, number 8. If y of t is another harmonic term, cosine omega t. So the Laplace of this, for God's sake, using the part-by-part integration from high school, I'm skipping that. Cosine omega t e minus st dt gonna be is the same like a sine. They have difference in the numerator. In the sine was omega, and here is s. The only difference is this. Now, for example, I'm asking you, please go ahead right now. I give you 2 or 3 minutes and calculate, guys, this. Calculate cosine of t minus 1. It's Laplace. What's the Laplace of y? Please do it. I'm here. The answer? It's very easy, huh? Remember, if the y was cosine 2t, your omega is 2. So its Laplace f of s was s divided by s squared plus omega squared, 2 squared, 4. But here we have what? You tell me. What is this I taught you today? What is this? T minus 1? Huh? So the Laplace of y t minus 1 gonna be e minus s in f of s. As I taught you, that's right. F of s we already calculated. S squared plus 4. Bingo. You got it. Okay. Now, number 8, number 9. If you have a given function as y is equal to f of t and its Laplace is f of s, so Laplace of e a t f of t, if you multiply by exponential term, I'm gonna select different colors, minus and plus, gonna be f of s a. I'm gonna select the same colors. Minus gonna be plus here, plus gonna be inverse minus here. Interesting, right? Example, if y is cosine 3t, I'm asking you what's the Laplace of e 2t cosine 3t. Please do it. It's very simple. Just use this and you can use 8 and 9 together. So we know that f of s, Laplace of this, gonna be s divided by s squared plus 9. But by multiplying to exponential term and it's positive gonna give you negative. You have to replace everything with s minus 2. Every s you have to change it with s minus 2. If you apply it here, you get this Laplace of e 2t cosine 3t. You have to change every s with s minus 2. See, s minus 8. S minus 2 divided by s minus 2 squared plus 9. Here we go. Clear, everybody? Yes? Everybody clear? Yeah, so see, when Laplace of f of t is f of s, if you multiply by exponential term, what happened? Oh, okay. If you multiply by the exponential term, you're gonna change the s's to s plus a if this is minus, or s minus a if this is plus. So cosine 3t, based on whatever I taught here, is s squared plus omega squared. Omega is 3. 3 squared is 9, right? Clear until this point? Yeah? But you are multiplying by e2t. Your a is 2. And the sign is positive. So you have to change all s's with s minus 2. S minus 2. All s's you got here, you have to change it with s minus 2. You got it now? Yes? Huh? So s minus 2. S minus 2 squared, and the rest is the same. Now examine this one. Yeah. Okay. What again? Yes, yes. Yes, yes, yes. I'm gonna just solve another problem, okay? Bear with me. So if y, suppose, is unit step, huh? Now calculate Laplace of e minus 3t unit step. We know that from the notes today, Laplace of this f of s is how much? Look at your notes, unit step. How much is that? Is 1 over s, right? Look at your notes, all of you. So now you are multiplying by this. So you have to change f of s with f of s, because this is minus plus 3. Look at here. This is minus plus. You got it? So if I do that, the answer gonna be, you have to change s with s plus 3. Here we go. Here we go. You got it? Yes? Everybody? Or if your y is ramp, I'm asking what's the Laplace of e10t in ramp multiplied by ramp. We know that from today's notes that the f of s is 1 over s squared. So you have to change all fs by s minus 10, all s's, because here's plus, get here, plus gonna be minus. So the answer is 1 over s minus 10 squared. I just replaced this here. Clear? Everybody? Yes? Good. And please do it now. I want to make sure that you learn. If y is sine of 2t, what's the Laplace transform of e minus 100t in sine of 2t? Just 2 minutes, do it. Answer? We know that from today that the Laplace of this is omega. Your omega is 2. Divided by s squared plus omega squared. 2 squared is 4. So by giving that means replace s with what? S plus 100. Because this is minus, this is going to be positive. So the answer gonna be 2 divided by s plus 100 squared plus 4. Simple like that. Clear, everybody? Can I go to next? Yes. Okay, number 10. If you have y of t given as input to the system, and I want to calculate Laplace of f prime, first time derivative of that, or df over dt. We know the Laplace of this is f of s by definition. It's Laplace. So it's going to be calculated as from 0 to infinity f prime of t e minus sd dt. Just use the part by integration Huh? How? I'm just giving you the hints. You can do it at home. You can say E minus ST is U, and F prime of T dt is dV. Use that formula I told you. U dV is VU minus integration V du. Find from here and put U. So if you do that, this is super important now, because I'm gonna back to the moving pendulum hopefully by next class and taking you to the Simulink. Okay, Simulink simulation in MATLAB. It's gonna be f of s and the function at time 0. This is how we calculate it. The most application that I taught you from the beginning of the class, I'm going to stick to this many times, is our moving pendulum. I said, assume that the disturbance to the system is impulse. So if we want to go to the Laplace domain, so I want to find the x dot, because you have to gradually come here, that's right? First time derivative. What is the first time derivative of the unknown? God knows. We don't have it in time domain. What we're going to do? We say, we know that the Laplace of impulse is how much from today class? You tell me. Look at the notes. How much is that? Laplace of impulse? How much is that? 1, right? Today I taught you. 30 or 40 minutes ago. From number 1, this is number 10. So Laplace of time derivative of impulse, or x dot, gonna be s f of s minus f at time 0, right? So it's gonna be s, because f of s is 1, minus f at time 0. Actually, we don't have it still. I just wanted to give you an example, okay? Another example. If y is sine of 40, what's the Laplace of its time derivative? Sine 40, first time derivative. Based on definition, is s f of s minus its value at 0 times 0. We know that Laplace of this, now you know it, is omega 4 divided by s squared plus 4, or plus 16, sorry. Where's omega squared? 16. So the Laplace of time derivative of this is going to be s 4s divided by s squared plus 16. What's the value of this function at time 0? What is sine of 0? What is sine of 0 from high school? 0. So we don't write it here. Bye-bye. We found that. There we go. And we have the proof of that. Why? Because time derivative of this from high school, it is 4 cosine 40. So the Laplace of this, based on whatever you taught today, is 4. And the Laplace of cosine 40 is s squared plus 60. And these two are equal. Here we go. So, but what we do care is this, for any function. For any function. Okay? Number 11. If you have a given function of time, Laplace of second time derivative means that you have to go part by part many times, at least 2 times, to find the solution. So the answer is s squared Laplace of the function minus s initial value at time 0 minus first time derivative at initial value at time 0. That's here we go. We're going to use it for electrical circuit, for mechanical system, for fluid system eventually in this course. For example, if y is e minus 2t, I want to find Laplace of second time derivative of e minus 2t. First of all, we have to find f of s. We know it from today's course. Is 1 over s plus 2. Here's minus, gonna be here's plus. So we have to find its value at time 0. At time 0, f of 0 is how much? 1. And f prime at time 0. So f prime or y prime is minus 2 e minus 2t from high school. At time 0, gonna be minus 2. So it's gonna be s squared f of s plus 2 minus s in 1 and plus 2. Here we go. This is the answer. Laplace of second time derivative of this. Okay. So I give you this example and I hope that you solve it now and we are done for today. If your y is e minus 3t sine 3t, what's the Laplace of y double prime? And I'm writing the general solution here. S f of s minus s f at time 0 minus f prime at time 0. So we know this, but this is multiplied by e minus 3t. Remember this formula? Where is that? By this formula. So you have to use this s plus a, remember? So the Laplace of this, the original function, or f of s, gonna be 3 divided by s plus 3, because of this minus 3, square plus 9. Everybody agree using this formula? That's right. Everybody agree? Yeah. So Laplace of this is going to be s squared in this. So going to be 3 s squared divided by s plus 3 squared plus 9. F of 0, sine of 0, 0. So it's going to be minus 0. And f prime, so y prime. Y prime going to be minus 3 e minus 3s sine from high school. Change rules, right? Plus 3 cosine 3t e minus 3t. First in second, second in first. At time 0, this is 0. and this is 3. Here we go. So minus 3. Minus 3. Bingo. This is the answer. You got it, everyone? Yes? You got it? For this part, for the original one, I use the formula of Fs plus A. Calculated this and implemented here. So, in the next class, I'm going to take you to the Simulink before going ahead and saying, if we have the moving pendulum with the disturbance, and the disturbance to the system is unit step, how are we going to make a Simulink model in MATLAB and take the graphs? Okay. By knowing that theta at time 0 is 0, initial condition, angular velocity at time 0 is 0, then I'm going to apply the next class Laplace in the both side of this, and we go to transfer function and frequency domain, and then go to MATLAB Simulink, and using Simulink to expose you how to work with industry. Okay? Clear? Everyone? So let me stop.